Hi, mini mathematicians, salutations. I'm so happy you could join us today. We're going to be continuing over stories and graphs. Let's print out 7.2e, apply features of graphs, 7.2d vocabulary to real world situations. So let's take a look. 7.2e, stories and graphs. So we're going to match the story with the correct graph. Lucy walked away from her house at a steady rate. She walked away at a steady rate. That lets me know it's probably something linear. And then we also are told here that she's walking away from her house. So, and the distance represents the distance from Lucy's house. So as she walks away, is she getting closer to her house or is she getting farther away? She's getting farther away. So the correct graph here is going to be graph A. You guessed it. Very good. It's a constant rate. This would be she's walking away and then maybe she's walking back towards because the distance increases and then decreases. This is her distance isn't changing over time. So she's not getting any closer or farther away, which means maybe she stopped to tie her shoe. And notice here, she's not starting at home. If the distance represents the distance from Lucy's house, at time 0, she should be at home because she's walking away from her house. And here it looks like she's starting far away and then getting closer and closer at a steady rate. But here she's starting at her house and walking away at a steady rate. Okay, let's take a look at the next one. Sunny walked toward the swimming pool at a steady rate. On the graph, each distance represents the distance from the swimming pool. And it's really important to think about what does that origin represent? What is that distance 0? So here, if we're walking towards the swimming pool at a constant rate, D is our only option because notice we have the same graphs as above. I'm going to show you a quick YouTube video about distance and time graphs. Cool. So that gives you a quick little overview of speed time, distance time graphs. Distance time graphs just talk about speed. So let's continue going. So Anna ran towards the beach and then walked away. And on each graph, the distance represents the distance from the beach. So why don't you read 3 and 4 and select your best one. So go ahead and pause me and we'll go over the answers in a second. Okay, so here, since we are running towards the beach and then we walked away, we're using C because we're steeper here, which means we're going faster. And then here it's increasing, we're walking away, and this is the distance from the beach. So we're getting closer, and then we slowly get farther away. Number 4. And no, I don't know why she ran towards the beach and then walked away. Maybe she forgot something. Number 4, Max stood still as the others were running. So obviously thinking about what is this origin? What is the distance representing? We're thinking the distance represents Max, right? Just Max in general. So this is definitely going to be C because he stood still, and this graph is all about Max. So why are the graphs above only graphed in the first quadrant? So maybe you remember that the coordinate plane or Cartesian plane is broken into 4 quadrants, like quad, the number 4. And it goes 1, 2, 3, 4. They like to use Roman numerals for this. I can write it with regular numbers though. 1, 2, 3, 4. Some people like to use a C to remember that. All students take calculus. So why are they graphed only in the first quadrant? Because remember, we're comparing distance and time, and both those values can only be positive. Distance and time can only be represented with positive values. Awesome. Let's keep going. So now we're going to use the distance time graph to answer the following questions. So very similar to that YouTube video that you just saw, we're going to be asking for the speed in different intervals, which is the fastest. So we're going to be looking at the slope and steepness of our graph. So what is the speed during the first 20 seconds? Well, the first 20 seconds from here to here, remember, speed is your slope. So what you could do is you could think about the slope from 0, 10 to 0, 20. And we looked at that as that the velocity or speed is the slope of a distance time graph. So the speed during the first 20 seconds, well, taking a look here, it's a horizontal line. So your distance isn't changing, which means your speed is 0. So we could say 0, and your explanation could be something like no change in distance. First 20 seconds. If you are super mathematical and jumped into calculating the slope, because maybe you did, and that's fine, we can say the rate is changing distance over change in time. And that's what speed is. And also notice change in y over change in x, distance over time. And you end up with 0 over 20, which is also 0. 0 divided by any non-zero number is 0. Starting at 0 seconds, what is the distance after 50 seconds? So I'm starting at 0 seconds, and then at 50 seconds, which is in between here, I'm going to go up. And that distance represents 30. So don't forget your units, 30 meters. What is the speed from 60 to 80 seconds? So this is 60 to 80. It looks like we are moving again. Looks like we stayed still. We walked away. We stayed still. We walked away. And then we walked back to whatever our 0 point is. So what's the speed from 60 to 80 seconds? So remember, rate is change in distance over change in time. We're using the delta symbol that looks like a little triangle for change in, just like we did with our slope formula. And our distance looks like we have 40 and 30. So I'm going to go, oh, it looks like this is 35, sorry. 35 and 30. So 35 minus 30. And 35 corresponds with 80, so 80 minus 60, which would be 5 over 20. which means we're traveling at about 0.25 meters per second. It's pretty fast. Quarter of a meter. When was the object traveling the fastest? So we want to look for the steepest slope. It doesn't have to be the positive slope, it just has to be the steepest. So looking from 60 to 80, that is a 20-second interval, and we traveled 5 meters. So from 60 to 80, we traveled 5 meters. But if we take a look from just 80 to 100, which is the same time interval of 20 seconds, we traveled, let's see, 10, 20, 35. So obviously this is the steepest part of the graph. We were traveling the farthest in the same amount of time. Woo! I don't know if that was as loud for you guys as it is for me in my headphones. 1 second, please. Okay, so taking a look, when was the object traveling the fastest and explain? So it's between, so that is, let's calculate that slope for us. So that is 35 meters in 20 seconds. And we're going to compare that. The only other slope we haven't calculated yet is from 20 to 35. And it looks like from 20 to 35 seconds is going to be 15 seconds. I guess it'd be 20 to 30 because it's halfway. So that's 10 seconds. And in 10 seconds, we traveled 20 meters. So what's faster? Traveling 20 meters in 10 seconds or 35 meters in 20 seconds? Well, if we doubled 10 seconds, if we went this rate for twice the amount of time, that'd be 40 meters in 20 seconds, which is actually farther and faster than 35 meters in 20 seconds. So taking a look at these slopes, which line is the steepest? It's going to be between 20 to 30 seconds. And say steepest line. You can also use your ratios and explain traveled the most distance in the same time interval. Awesome. So let's take a look, and what we're going to do is we're going to draw a possible distance time graph for the story described below. Obviously, our graphs aren't going to be exactly the same, but they're going to look really similar because we're describing the same story. So taking a look here, let's read the story first before we start graphing, just in case we want to add something and we want to know like how far we have to graph. So Stacy walks at a constant rate. That's important because that means it's going to be a linear relationship from her house to the bus stop. You know, this is distance from her house. So she's starting at home, which is really important to know. She sees the bus coming, so she runs. Oh my gosh, so that means she's going to be faster. So we're going to have to make that slope steeper. At a constant rate, so still linear, to catch it. She gets to the bus stop, but misses the bus. Ain't that the way things go sometimes? After a short rest, meaning she's not going farther away from her house or getting closer, Stacy turns around and walks back home at a constant rate. So maybe this walking and this walking might have a similar slope to it. Okay, so we are going to start walking, and then Stacy sees the bus, so she's gonna run. Run, Stacy. And then she misses the bus, so she's going to have a rest. And then she's going to walk back home. And she's back home. So maybe your graph looks something very similar. We have an increasing linear relationship, then we have an increasing more, we have a horizontal line, and then we have a decreasing line that's very similar to our first part. And sometimes what I like to do is I like to label, because since it says in the directions, label your starting point and ending point and parts. So we say at home, walk to bus, run to bus, resting, and sad resting, walk home. So it's nice to be able to label our story with our graph to make sure they correlate. Okay, so what does the graph look like when Stacy walks from her house to the bus stop? Explain why. So when she's walking from her house to the bus stop, it's a positive line because walking away from house. As time increases, distance increases. Okay, the next one says, what does the graph look like when Stacy walks home? Negative slope. Decreasing line. She is traveling towards home. As time increases, distance from home decreases. What happens to the line if Stacy runs? Well, if she runs, it's going to be steeper than when she walks. Line is steeper. What happens to the line when Stacy stands still? Horizontal. Zero speed, zero slope. As time increases, distance does not change. You can say stays constant. Awesome. So there's a little example of creating a distance time graph from a real world situation with our friend Stacy. Okay, let's take a look at some other real world situations. So we have Cynthia. She's doing research on how hot coffee is when it's served. And at one coffee shop, she was served coffee that was 180 degrees Fahrenheit. Cynthia bought the coffee and then left it on the counter to cool. And the temperature in the room was 70 degrees Fahrenheit. And the graph shows the temperature of the coffee in degrees Fahrenheit as a function of time in minutes since it was served. So notice this is the initial temperature, and it's going to cool down and then kind of level out about at room temperature, because as if you have a drink, it can't get colder than it is in the room or necessarily hotter than it is in the room, because it's going to just kind of balance out that ambient temperature. So we're going to include a story, include statements about the temperature just from this graph. So just from this graph, a coffee is served at 180 degrees Fahrenheit. The temperature of the drink decreases. And does it decrease just a little bit? Does it decrease steadily at a constant rate? Or does it decrease really fast? So notice from here to here, it only decreased this much. So it looks like it decreased rapidly, and then the decrease starts to like level out. The drink decreases, temperature of the drink decreases rapidly, so not at a constant rate, fast. And then decreases at a decreasing rate. Until, and what that means is every 2-second interval, we're still going to decrease from the previous temperature, but we're not going to decrease as much. So maybe we're decreasing by 40 degrees, and then we're only decreasing by 20 degrees, and then only 10 degrees, and then only 4 degrees, and only 2 degrees. So then decrease that decreasing rate until reaching about room temperature, 70 degrees Fahrenheit. Nice, and then it'll stay there. It's not going to continue decreasing and turn into an ice cube just by sitting on the counter. That'd be weird. Number 9. So, ooh, parabolic motion. I see it. Makes me think of playing cornhole. Okay. A toy rocket is launched straight up into the air from the ground. It leaves the launcher with an initial velocity of 96 feet per second. The graph shows the height of the rocket in feet with respect to time in seconds. So what we want to talk about is we want to talk about a couple really important things. We want to talk about when the rocket's launched, that it's on the ground. We want to talk about its maximum height and how long it took there. We want to talk about its total flight time, and I guess that's what we're going to talk about. So, story. A rocket is launched from the ground at 0 feet. So as the rocket ascends, it's going to rapidly ascend, and then it's going to increase at a decreasing rate. So notice for the first second, it increases about 80 feet in 1 second, but then at the next second, it only increases about 40 feet, maybe a little bit more, 50 feet. And then the next second, it only increases for a little bit more than 10. So the rocket goes up into the air. So word for going up into the air is ascending, because when you come back down, you're descending. Ascends upward, increasing its speed at a decreasing rate. At 3 seconds, maximum height is achieved or reached at 144 feet. The rocket descends and notice as it descends, it's going to get faster and faster as it gets closer. So increasing its speed at an increasing rate until it hits the ground. Total flight time is 6 seconds. So some really important pieces of information to use when you're talking about the launch of a rocket in that parabolic motion. Okay, so let's see. B Bytes is releasing the most anticipated new Xbox game of the summer. The graph shows the total number of games sold as a function number of days since the game was released. Story includes statements about game prices. So taking out here, when the games first release, games are being sold at a high rate. When the game first comes out, people are excited and buy lots of games. But then as time goes on, people already have the game. And more new games come out. Sales of the game increase at a decreasing rate. Meaning we're not going to sell less games. Obviously, they were already sold, but they're going to increase maybe at a lesser amount. And maybe as time goes on, the price of that game decreases, so people will still buy it because it's maybe cheaper than other ones. But yeah, that explains our B Bytes most anticipated Xbox game of the year. So now what we're going to go into is we're going to go into the reverse of that. I'm going to give you the whole story, and you're going to give me the entire approximate graph of what that could look like. So remember, it's really important to read the entire story before you start sketching, because you might realize, oh, this part has to be steeper than that or less steep. And it's a little bit annoying to go back through and erase everything on the little graph. So let's talk about Zach. Zach's walking home from school. And notice this is distance from school. So we're starting at school because we're walking home from school, distance from school. So we're starting at school. So we can even say that. Start at school. I still find labeling my graph really important. Zach walks home from school. When the bell rings, Zach runs to his locker to grab his books and starts walking home. When he's about halfway home, he realizes he forgot his math book. So he turns around and runs back to school. After retrieving his math book, he realizes he's going to be late. So he sprints home. Sketch a graph of Zach's distance from school as a function of time since the bell rang. Okay, so eventually we're going to end up at home. So maybe your home is here. And we want to think about a distance that's about halfway. So that's about halfway in the distance department. So we're going to start at school. And when you run to your locker to grab your books, you're still at school. Your locker's at school. So we are actually going to stay at school. Our distance from school is not going to change because we're still at school. Your locker's at school. And then you're going to start walking home. So now we're going to start walking home, and you're going to get about halfway. So walking, and we said that this was a distance about halfway. Doesn't matter about the time, it matters about this distance. And then, oh no math book. quick, run back to school. So steeper. And then you go to your locker, you retrieve your math book. It took you a little bit while you're at school. And then you're going to sprint home. So it has to be faster than a run. So I'm going to go super fast. Let's make this dot bigger. Home. So let's see. So we're going to walk to locker. Walk to locker, still at school. Walk home. Run back to school for your precious math book. And then you're going to sprint. Sprint home. And here you're going to retrieve precious math book that you love so much. You love your math book. Okay. So let's talk about Solitude Ski Clinic. So we have a ski clinic, and notice we have revenue and we have number of students. We might have to talk about the word revenue, so let's keep reading. Solitude is offering a ski clinic for teens. The cost of the class is $30 per student. A minimum of 5 students must sign up in order for Solitude to hold the class. The maximum number of students who can participate in the class is 12. Because ski instructors can't instruct so many kids. Sketch a graph that shows the revenue Solitude will bring in dependent on the number of students that take the class. Well, 30 times 5, if you have 5 students paying $30 each, that is $150. And then we can have a maximum of 12. So 12 groups of 30. $360. But notice that we are going to be going discretely. This is going to be a discrete graph because between 5 and 6 students, we're not going to make any money in between. It's either you have 5 students, you're making $150, or you have 6 students, you're making $180. So if you wanted to think about it that way, making a table of students, notice that's the x-axis and that's the y-axis, and revenue, we're going to start at 5, 6, 7, 8, 9, 10, 11, 12. And our revenue is going to be changing by 30. So we have 150, 180. We know that this is 360, 210, 240, 270, 300, 330, 360. Okay. So, taking a look here, we're going to have a discrete graph. Between 4 and 6 is 5, so I'm going to go to 5 and then 150. Here-ish, 6, 180, 8, 240, 9, 270, 10, 300. And notice this is going to be a linear relationship. 11, 330, 12, 360. And it should be linear but discrete and linear. So note that this is discrete and linear. Cool. It's hard to graph without lines, but I think we did a nice job. Okay, so a parking garage charges $5 per hour and a flat rate of $40 for 8 or more hours. I mean, having a parking garage seems like a pretty good, profit-wise. You don't have a lot of upkeep. People just park there. I don't know, might be something to look into in investments. Parking garage charges $5 per hour and a flat rate of $40 for 8 or more hours. Sketch a graph for the total cost depending on how many hours a car is in the garage. So parking garage is also If you park there for 5.5 hours, the good parking garages, especially if they're charging a flat rate for 8 or more hours, they're going to charge you for that partial hour. They're not going to round up and charge you more, which is really nice. So we're going to assume that's how this parking garage is. It charges for partial hours. And by making that assumption, we're going to say that this graph is continuous. Okay, so if we parked for 0 hours, we're going to pay $0. Like we came in, we drove around, we're not going to stay. For 2 hours, we're going to get charged $10. For 4 hours, we're going to get charged $20. So we're going to go over 1 up 2, over 1 up 2, over 1 up 2, over 1 up 2, all the way to 8. But then from here on, we're only going to get charged $40. And we can connect our graph because it is continuous since our assumption that we made. So that's a little bit of practice applying our features of graphs. I hope you are having a great day. I hope you continue to have a great day. Do your best. Be nice to everyone. Video bar out. Do you like my little sparkles for you? Just wanted to shine a little bit.